Welcome everyone to the Concrete Educational Series brought to you by Carolina's Ready Mix Concrete Association in partnership with both the North Carolina and South Carolina Department of Transportations. So to begin, our series will focus on sustainability initiatives across the concrete industry, beginning with the following topics: Cradle to Gate, an introduction to concrete, evolution of customer expectations, an overview of LCAs and EPDs, ending with innovation and materials. Welcome, my name is Jessica Wilson. I'm the Director of Technical Services and Education for CRMCA, and we appreciate your time. To begin, let's start with the foundations of sustainability knowledge. The course purpose is to equip attendees with the knowledge needed to navigate shifting customer expectations, meet sustainability goals, and adopt forward-looking practices in concrete design, production, and project delivery. Our learning objectives are the following: address the tenets of sustainability, exploring approaches to stewardship and defining key terms used in sustainability language, identify key components and raw materials used in concrete production and explain their roles in the manufacturing process, analyze the operational workflow of a concrete production plant, including batching, mixing, and quality control procedures, evaluate the supply chain dynamics involved in concrete manufacturing, including sourcing, logistics, and distribution considerations. Assess the environmental impact of concrete production with particular emphasis on carbon footprint and sustainability challenges. And explore carbon reduction strategies through benchmarking, mixed design optimization, and cross-collaboration. So to begin, let's put things into context as to why we're talking about concrete. Global usage and demand of concrete is of top priority. Concrete is the second most consumed material on the planet after water. Over 4 billion tons of cement is produced annually at the global scale. 32 billion tons of concrete is produced annually, which attributes 7 to 9% global CO2 emissions. So the opportunity to improve our industry from a carbon standpoint is vast and necessary. Concrete is both a carbon contributor, but also an absolute necessity in terms of building materials. So let's begin with sustainability tenets. Let's start with the triple bottom line and where sustainability was essentially derived from. So the triple bottom line was a foundational approach to sustainability that included three tenets or three pillars that impacted the bottom line. And typically they're referred to as: how is your product or your process impacting your community or your people? How is it impacting the planet or the ecosystem? And from an economic standpoint, how is it impacting your profit or your bottom line? But this goes beyond your traditional P&L statements that typically just looked at profit and losses to looking at how a business and or a product impacts its entire ecosystem. So we're looking holistically at how concrete, again, impacts those three main bottom lines. But from a DOT consideration standpoint, we're focused on resource responsibility and resource scarcity. And before we move on, I do want to talk about how essentially an entire globe looks at sustainability. It's through the UN's Sustainable Development Goals. And so that was established in 2015. There are 17 goals that the entire United Nations agreed upon that would help us propel our future in a sustainable fashion. From an industry perspective, those goals from a UN and sustainable development perspective, our concrete ecosystem is predominantly focused on achieving 9, industry innovation and infrastructure, 11, sustainable cities and communities, 12, responsible consumption and production, and 17, partnerships for the goals. Now, addressing concrete and cement particularly, as you'll hear later in the series, cement is the major contributor to carbon in concrete. The Portland Cement Association, now ACA, has established ambitious goals for carbon reduction across the cement and concrete construction value chain with an industry-wide roadmap to carbon neutrality by 2050. So before we start looking at ways we can achieve carbon neutrality by 2050 throughout the series, we need to define classic sustainability language that is oftentimes utilized in discourse. First, let's define embodied carbon. Embodied carbon is the total amount of greenhouse gas emissions measured in CO2 equivalents, or CO2e, that are associated with the production, transportation, installation, maintenance, and disposal of a product or material over its entire life cycle, excluding emissions from its use phase. So essentially, the green building narrative has focused on operational carbon, which is after the building or the project is completed. What does it look like from a CO2 standpoint to operate a facility? So we've been focused on managing and measuring and reducing said carbon emissions from an operational standpoint. But now the narrative has focused to include embodied carbon, which actually accounts for more carbon over the entire life cycle of a project or building. And that, again, is all of the associated carbon emissions of the raw extraction and manufacturing process of materials, even transport to a job site. Carbon budget is the second term that you will hear amongst sustainability professionals, especially when we're talking about calculating the total carbon that is allowed for a project. So oftentimes this is also referenced to as carbon accounting. And again, a carbon budget and a carbon accounting is a carbon accounting principle, I should say. And it's the maximum amount of greenhouse gas emissions typically measured in CO2 equivalents, CO2e, that the project can produce over its entire life cycle in order to meet environmental or climate goals. Also, when we're talking about a project or a building in particular, we see GWP mentioned in specifications. And GWP is called global warming potential, and it is a standardized way to measure and compare how different greenhouse gases contribute to climate change relative to CO2. Life cycle assessment. Life cycle assessment is a systematic method used to evaluate the environmental impacts of a product, process, or service throughout its entire life cycle, from raw material extraction to disposal. And our first session in the series of educational offerings discusses the phase of cradle to gate, meaning that material manufacturing process, the extraction process, and the transportation process of a material from facilities to a project site. EPD stands for Environmental Product Declaration. An Environmental Product Declaration, or EPD, is a standardized document that provides transparent, verified, and comparable information about the environmental impact of a product through its life cycle. And so, in order to get a verified EPD, you must complete a life cycle assessment for whichever product that you are utilizing. So it's not specific to concrete. You can also have a life cycle assessment done on other materials such as steel or wood, for example. And with that being said, I would like to begin our first series and session with Kesia Kimmons from Titan America, covering cradle to gate concepts and origin of concrete materials. Thank you.
Thank you, Jessica. In this segment of the presentation, we will review the cradle to gate concept. Cradle to gate refers to the life cycle stages of a product from raw material extraction to the point it leaves the manufacturing facility. But it does exclude transportation to site, construction, use, and end of life. In reviewing the cradle to gate concept, why does this even matter? What this concept does is it helps identify environmental hotspots, such as cement production being a major source of CO2 emissions. It also supports sustainable procurement. As mentioned on the previous slide, it helps with developing EPDs. It enables policy compliance, such as the Buy Clean efforts. It drives innovation, which encourages low carbon materials and energy efficient processes. And it also establishes a baseline, which forms the foundation of the full life cycle assessment process. In this one, you'll hear a lot about carbon or understanding carbon. In this presentation, we'll be focusing on the embodied carbon, which covers the manufacturing, transportation, and installation of construction materials. In the future, you may hear more discussion of operational carbon, which addresses the building energy consumption. Cement versus concrete, what's the difference? Well, we know, those of us in the industry, that the terms cement and concrete have often been used interchangeably. As I introduced myself, I work for a cement manufacturer. It's not rare that we get a phone call for someone to say, can you deliver me a tanker of concrete? Or vice versa, a ready-mix producer being called for material and they say, can you deliver me a truck of cement? So we understand that widely in the industry, these terms are interchangeable. But when we look at it, there's a clear distinction between the two products. We know that cement is a binding agent made by heating quarried limestone and silica in a kiln up to 2,700 degrees Fahrenheit. This process results in clinker, which is later finely ground, and that is what it produces cement. We understand that concrete is a composite material made by mixing. This material includes cement, water, aggregates, of course, pozzolans, and other materials such as admixtures. We understand that the cement acts as the glue that binds this mix together. As mentioned earlier by Jessica, we understand that cement manufacturing's contribution to CO2 emissions globally is anywhere from 7 to 9%. We also reviewed that in 2024, 2.9% of that representation came from the US. Let's look at it from this viewpoint. In 2024, the US consumed 110 million metric tons of cement. This is roughly 880 plus million cubic yards of concrete produced annually. Even though in this chart you see that this is a 2017 date, as I reviewed over the years, for the last 8 years, this consumption or contribution in emissions has remained consistent with that 7 to 9%. This is impactful and important as we evaluate the growth of the US construction era. It's often been said that if we consider where we will be in 2050, is that we'll be adding 121 billion square feet of buildings by that time frame. This is equivalent to building New York City annually for 20 years. On a global scale, it is equivalent to building New York City every month. Again, as I referenced the interchangeable terminology of cement versus concrete, the importance of us addressing that leads to the concept of global warming potential and the impact that this terminology has on the ready-mix industry. When we look at the embodied carbon of building materials, you can see that concrete contributes 0.1 of the lower relative intensity of carbon. But as we look higher on the scale, you can see that cement has a normalized carbon intensity of 1.0. One would assume that the production of concrete at a ready-mix plant has minimal CO2 contribution. But unfortunately, due to the fact that they consume or utilize cement, they also are tagged with this interchangeable concept with that 1.0 contribution that takes place at the cement manufacturing process. What we understand is that this low relative intensity of carbon produced at a ready-mix facility is really contributed to dilution by way of supplementary materials, water, sand, aggregates. All of these components reduce the embodied carbon per unit volume of concrete. Now, as we move into the production process of both cement and concrete, We want to start with the cradle concept, which is at the quarry. We understand that 70% of the raw material that's used for clinker comes from our limestone quarry. That process includes survey, blasting, excavation, and of course, crushing that larger stone. Within the quarry, we're looking for three key elements: material that's high in calcium, greater than 95% calcium carbonate. We do look for dolomitic material which has magnesium. And then we also have lower calcium material that's less than 80% calcium carbonate. The impacts of this process produces dust, there is some CO2, habitat loss, and water use. For many of these facilities, the solutions are reclamation, dust control, water recycling, and renewables. Clinker is the core of cement production. Clinker is the main ingredient in cement. Again, it's formed by heating limestone and minerals in a kiln. You heard me mention earlier, the kiln can reach temperatures up to 2,700 degrees Fahrenheit. This is a high heat process that transfers raw materials into the product that you see on the screen. But it's also highly energy intensive, and it is our main source of CO2 emissions at a cement plant. Here we have a graph that kind of walks us through a cement production process. Obviously, everything starts at the quarry where we mine our raw materials. It then moves to the crushing component at the site. As that material is then crushed, it moves to the pre-harmonization and raw mill grinding facility. There, these materials are blended, and other materials such as iron ore, slag, and etc. are blended with that limestone material. From there, it moves to the preheating towers. Again, we want to get to that 2,700 degrees Fahrenheit, but we don't want to just wait till we get to our kiln to get there. So this material that sometimes is stored outside is then preheated and dried out before it gets to the precalcining tower. During the precalcining tower process, that uses the hot gases from the kiln, and it initiates the chemical reactions before those materials go into the clinker production in the rotary kiln. As it goes through the kiln, it is converted into almost the thought of a lava. At that point, the true clinker formation takes place as far as the chemistry. It moves there to the cooling and storing tower, in which this material is cooled down to less than 200 degrees, which is where you start getting the formation of the balls in the photo that you saw on the previous slide. Once it goes through that cooling process, it goes into the storage, and then again it is blended. During that blending process, it then goes through the grinding process. The grinding process is where you start getting the differentiation between a type 1-2 or a type 3. As the longer that it's ground, the finer that it gets, it changes into those various cement types that you are accustomed to. On this chart, they did not show that it does go through a finish mill, whereas at the finish mill is where your additional limestone is added. For some of your 1P products, the fly ash or slag, if there's a cement slag material that's being made, is all added at your finish mill. Once it moves from your finish mill, it goes into your storage cement silos that then are utilized to load your various tankers or your rail cars. As I mentioned previously, during that kiln preheater, precalcination process is the most intensive use of energy and the most higher distribution of CO2. As we see here on the chart, when we're looking at the raw materials with the energy and resources, we're looking at about 3% CO2 distribution. And that's mostly from the trucks and etc. the equipment that's moving from one location to another. But here you can see as it goes through the chemical calcination process, which means it goes through the preheater and precalcinator, you can see that that energy ramps up to 51%. And then as it's coming through the kiln, it consumes 34% of that. So 85% of our CO2 emissions at a cement plant takes place in that very process. And then once that material comes through the cooler and moves through the cement mill and the logistics process, that goes back down to a 12%. So as we look at the contributor, there are a lot of things that are being developed and are currently being used at a cement manufacturing process to reduce that impact of that 85%. As mentioned earlier by Jessica, she mentioned the PCA's 2050 roadmap to carbon neutrality. Here you see I have in parentheses ACA, as the PCA has changed their name to the American Cement Association. With that, in this roadmap to neutrality, there was the discussion of the value chain. And in this value chain, there are several different processes that are to take place so that we can find ourselves in a reduced or carbon neutral production cycle. You start with the clinker, which we just went through the production process of cement. We look at the variability of cements. There's also a move within the concrete industry. We look at construction service life and the use of phase impacts. And then final carbonation, which we look at the concrete as a CO2 sink. Specific to cement production, what we're looking at is replacing our raw materials with decarbonated materials like fly ash and slag. The use of alternative fuels such as wood chips, tires, hydrogen, recycled waste to move us off of coal or even natural gas. When we look at improving our efficiency, implementation of a CCUS, promoting the increase in the use of blended cements, transitioning to more renewable energy sources, developing possibly electric kilns and electrochemical processes, and utilizing concrete as a carbon sink. As I mentioned in previous slides, you saw we ended at number 10. Here we pick up into number 11, which is our transportation. As I mentioned previously, once our product is put in its storage silos or transport silos, we have the capability of loading tankers and rail cars. But we also have the capability of offloading vessels, as well as for some of our customers in the ready mix, they have the capability of receiving barges. As we move from the cement plant and we're making our deliveries to our ready mix producers, there's a little change, as I mentioned earlier, about cement and concrete, the term being interchangeable, as we look at how embodied carbon is reviewed in concrete. This flow of material, as we start with the mining of the raw material at the cement manufacturing at the quarry, and then we talked about a little bit about the consumption and the CO2 emission that takes place with the manufacturing process, which involves the limestone, the heat, and then eventually we are creating a clinker. But now as we move into transport to the mixing of the concrete, where there's air, water, aggregate, and cement involved, and of course, SEMs can be a part of that. You can see on this chart where it's almost like a little perfect U that what comes from cement manufacturing then moves its way into the component of concrete. And again, we remember that for every pound of cement that is manufactured, there's an estimate that there's a pound of CO2 that is emitted into the atmosphere. We know that concrete has, again, this is terms, concrete has high emissions due to Portland cement, which is greater than 90% of the total. Reducing cement use is the most effective way to cut concrete's carbon footprint. I'll repeat that. Reducing cement use is the most effective way to cut concrete's carbon footprint. Many of you, I'm sure, are aware of a ready-mix plants process. Here, we'll kind of walk through that process. We know that materials are delivered, which means the cement is delivered. We know the aggregates are delivered. We know that any pozzolans, fly ash, slag, etc., are also delivered to the site. From there, that material is then moved from stockpiles or moved out of silos into various chambers in which the various aggregates that are being used on that mix are then moved up a conveyor belt and then find their way into the ready mix trucks or the mixers. So we look at the first process as being batching or measurement of materials. That takes place a lot on the conveyor as the batch operator inputs into the system what mix they're using for that particular day or for that particular delivery. The mixing takes place within the mixer truck, and then that truck, of course, transports that material to the designated project site. We know that during delivery can take place in a directly into the project location by way of the chute of the truck, or it can be delivered into a pump truck in which the chute of the pump then disperses that material to the job site. Now, interesting enough, in this production process, they include placing, compacting, curing, and finishing as all a part of the concrete production process. But if I was to speak on behalf of Ready Mix, one would argue that where number 4 takes place is kind of where the Ready Mix producer stops. The contractor takes over the process of placement, compacting, curing, and finish. What we know today is that yesterday's concrete is not today's concrete. We are seeing a move from more of the simplistic concept of concrete placing, as it was coarse, fine aggregate, cement, and water. And as you can see today, we've moved into fibers, integral color, various admixtures, alternative SCMs like nanomaterials, alternative cements, water or treated gray water, recycled or low carbon aggregates, and etc. So today we have added several nuances in concrete that has to be managed, has to be balanced, and of course, all of those involved would need to know a little more about these materials as we move forward in what is considered today's concrete. This is probably a chart that you all are mostly accustomed to. We know that we've got gravel, of course, aggregate, sand, water, cement, and then air. This I would kind of consider the norm, or going back into a little bit of yesterday. But as you can see, Portland cement seems to be more of the foundation. As we spoke of earlier, it is the binder. And then you have all of these other components outside of course, what we're accustomed to, the aggregates, the water, etc., that also play a part in creating concrete as we know it today. I chose to show this chart is what we are seeing is more and more use of concrete, specifically in concrete paving, in structures, etc. This particular concrete parking in ICF school shows intersections, of course, obvious curb and gutters. We're seeing more concrete streets, heavy duty driveways, light duty parking, Foundation, floors, and walls is pretty common, flat work. But you've got your light duty parking, and then in the back of this structure, heavy duty parking. So for someone like me, this is a beauty, a beautiful picture, as it is all things concrete. When we think about moving forward or forward thinking, I spoke a little bit earlier about what were some of the things that we as a cement manufacturing facility would be looking at, as I mentioned about alternative fuels, as I mentioned about underground storage, that was the CCUS, as I mentioned, hydrogen and some other things that are being evaluated, and how we can drive down our CO2 contribution as a cement manufacturer. And all of the nuances, AI, and all of the things that a lot of companies are going with. We are utilizing that technology even at our cement plants. But we don't talk a lot about what would be the future of a concrete plant. And so here I've kind of given you a typical ready mix plant photo, but kind of put in some of the things that are really either currently being implemented or being evaluated. And we'll start at the far top left with negative CO2 aggregates. That can be that of recycled aggregates and etc. Digitalizing plants. Many systems have moved to the digitalized efforts, not only of maintenance, but maintaining various information about their materials. That is being implemented today. Of course, return concrete upcycling, automated job site acceptance, automated QC with AI, that is being done today, in the concept of reducing over design. Now, this particular segment falls a lot into updating specifications into performance based rather than prescriptive. Looking at higher performing concrete, taking advantage of some of the concrete options of today and getting the same expected results on many of our I guess you would say, high value projects. The concept of battery electric or hydrogen trucks, ready mix trucks, is also being reviewed. Renewable electricity, novel admixtures, ultra low CO2 blended cement with calcined clay or harvested coal ash. The harvested coal ash is actually being utilized today. And then again, you'll see the term CCUS, alternative fuels, and of course, the alternatives with clinker and cements. I'll turn it back over to you, Jessica, as I'm sure we have some questions for our presentation today.
Thank you, Kesia. Do we have any questions from the group today? Feel free to chat it. And as Caroline's monitoring the chat function, I do want to kind of revisit again the course purpose. And the primary reason for walking through the cradle to gate process, the raw material extraction, the manufacturing process, and the delivery and transport of materials to not only the concrete facility, but also to a job site. That is really a foundational knowledge piece that will aid you in the next series, which is around customer expectations, because the shift from, as Kesia mentioned, from prescriptive to performance-based specifications is definitely happening. And with that being said, we have to consider all of the carbon emissions associated with the process that we just covered in today's session. So as you can imagine, that's just mainly focused on cement. Imagine the processes and the global warming potential for materials that are included in concrete as well. So with that being said, that will again kind of build out your foundational knowledge so that when we talk about shifting consumer expectations, you also understand the onus that's placed on the cement manufacturers and concrete producers to manage and measure their carbon impact. So it's quite a lot to consider when we're talking about all the emissions associated from the cradle to the actual gate. And that doesn't even include the end of life cycle carbon implications either, which is called the quote grave. So that's a whole nother topic. But any questions on the process for cement manufacturing or the terminology or the cradle to gate concept?
Jess, I have one question. Does the CRMCA have its own lab for testing materials used in concrete?
Caroline, you can answer that too, but no, we do not currently. We rely on the producer partners for labs, and also MIT has a pretty substantial lab that is a national laboratory. Do you want to add anything, Caroline, there?
Nope, I think that's perfect. Access to some other ones through producers and then obviously the testing firms as well.
I would like to add that many of testing that cannot be conducted with producer labs, they do utilize the National Ready Mix Concrete Association's lab in Maryland for extended testing.
There you go.
Excuse me. Yeah.